In this video, I'm going over some practice problems with our exponential and logarithm functions. So these first couple of questions have to do with the application of the exponential functions. So here, as you're reading through, we're depositing starting with that value of $6,000 and no further deposits or withdrawals are made. The account receives a 3.5% annual interest rate. Or remember, right, divide this by 100, move the decimal 2 times to the left. So that's why here you get 0.035 as your rate. However, notice how we are compounding. So now whenever you have compounding, we do have that value for n. Then what follows is tells you how often. So compounded monthly, where you get n is 12. So if no further deposits are made, then what's the amount in 6 years? So remember, first off, if you're compounding, we have this n value of 12. So I'm going to go ahead and mark off A. I can also go ahead and mark off B because notice how we got the wrong rate here. So now we're down to B or C. Well, I notice the difference between the two is the exponent. So if you recall, we do raise to the 6th power, but don't forget you also have to multiply by that n value of 12, which is why the exponent is 72 and the answer is C. Now in question 2, we are actually calculating. So you're starting with that principal original amount of $1,800 being deposited. You have an account that pays 5% interest or 0.05, right? Divide by 100, move the decimal 2 times to the left. And again, compounded, so we have another value of n, compounded quarterly, which means n has a value of 4. What is the balance after 8 years? So 1,800 times 1 plus, now remember with that value of n, we need to divide our rate by the value here, how often the account's being compounded, or the rate. And then don't forget to raise to the not just 8th power from the time, but 8 times 4, that value of n, which means really the exponent is 32, not just 8. So now putting all that in the calculator, you get an approximate amount of $2,678.64. Now in question 3, you are just again converting, guys. Notice how we have log base 24 of 8. So this is using our change of base formula, where again we are dividing our two logs here. So again, I need log of 8 divided by log of 24 here. Base needs to go in the bottom here. So now when you set that up, and divide, so log of 8 divided by, as I'm putting this in my calculator here. So we have log of 8, then divide that by the log of 24. You end up with approximately 0.654. So then in B, again, setting up that change of base here. So now here we're going to end up with evaluating log of 141 divided by log of 16. So when you put that in the calculator, you end up with approximately 1.785. Now here we are converting this exponential to a logarithm. So this is our log with a base of 12 because that's the base of our exponent, the exponential. Log base 12 of y is equal to your exponent always, right? Which in this case is x. So again, remember your exponent is always what the equation is equal to. So then here we're writing the inverse, but now given the log, we're going the other direction, which is the exponential. So again, your base of a, remember your equation is always equal to the exponent, so that's a to the c is equal to 7. So same thing here, you have a base of w, so w to the third is equal to 24. That is the inverse. Now here, when we're solving, notice how We have a common log with that base 10. So to solve for x, we need to convert it to the exponential, which is 10 to the 6th power. When you put that in the calculator, you'll get approximately, or not approximately, you'll get 1 million. So then here, now notice we have a natural log. So if I'm trying to get the inverse here to solve for the natural log, you're going to end up with e. So this is now e to the what power? Well, e to the 5th power. And that is approximately 148.41. Functions, like as if we were finding the inverse, right? So thinking about like if I were to look at D here and see if D has a solution of -3. Well, just like getting the inverse, the exponent has to be by itself. Well, right now, 10 to the x is being multiplied by 2. See how we're multiplying by 2 on the outside? So that I need to divide by 2. Inverse, opposite. We're solving the equation here, getting the inverse. Now 10 to the x is equal to 100. So now we could actually use mental math here. 10 to the what power is equal to 100? Well, x is equal to 2 because 10 to the 2nd power is equal to 100. Now you could also continue writing this as the inverse. So I could write this as my log. So log, what's the base? Well, the base is 10. The log base 10 of 100 is equal to x. So now notice we're back to that change of base here, where I have log of 100 divided by log of 10. So when you put that in the calculator, you do also end up with 2. Then we could also check our work by graphing in Desmos. Even though this is not a radical, it's still an equation. So a same thing, you're going to graph the left side here on the first line, and then 200, but not just 200 on the second line. Y is equal to 200. And then see where the two graphs cross each other. They should cross each other at the x value of 2. So let's see. So here, notice, and if you need to, after you graph it, right, change the window because we have that value here of 200. So where are these two graphs crossing each other? Right here at, at x is equal to 2. So now going back, I notice then the answer clearly is not D, right? Because we got x is equal to 2 and we showed that. So now I can go to check A. Well, let's just go ahead and graph it. So here, I'm going to go ahead and graph on line 1, and then graph here on line 2, but make sure again that this is y equals that value. So as I go back to Desmos here, so I went ahead and already graphed those. Let's see. So now I need to change my window here. I'm going to zoom back in. So now I can see right here, my two graphs cross each other. At what point? -3, 0.75. So notice what is the x coordinate? -3. So that means x is equal to -3. So that's why here the answer is A. Now in question number 7, you're looking to see which of these graphs represents our natural log of x minus 5 plus 6. So here we could go directly into graphing in Desmos and seeing where our graph, which graph matches. Now I notice, sorry about that, I just realized I did that. Here, as I'm looking down, I do notice that I've got asymptote here at 5, but now going here, increasing, but in this direction. And here we have an asymptote at -5. So now keeping in mind, let's go ahead and take a look at the graph here. Well, I already noticed I have this asymptote at 5. So I'll go ahead and mark off C because it has the asymptote, vertical asymptote at x is equal to -5. I also noticed too by the direction that here we are increasing and going on to the right into positive infinity. So that means I'm going to mark off D. Then also noticing here that we do have above the x-axis and into our positive infinity. So that's why here the answer is B, because notice how here this graph is in the negative values. Now you could always check too by comparing points on the graph and making sure that they match as well as to what you graphed. So now in question number 8, this is going back to solving our radical equations, which again, you could graph the left side on one line in Desmos, graph the right side in Desmos as well. So here I'm going to solve this algebraically. Now notice we have the radical by itself, so we can go right into squaring both sides. So now radical cancels out, and here I've got 6x squared minus 2. Now notice here we've got x plus 1 squared, which is setting up our box method or FOIL, because that's x plus 1 times itself x plus 1. So now here I've got x squared, now just 1x. Here I've got 1x, and 1 times 1 is 1. So now I've got x squared plus 2x plus 1. Now, here we are solving a quadratic, and quadratics always have to equal 0. But I notice I have 6x squared here, so I'm going to move everything from the right side over. So I'm going to subtract x squared from both sides, subtract 2x, as well as subtract 1. So now we've got our quadratic here equal to 0. Combining like terms, 6x squared minus x squared is 5x squared. Now notice there is no other x term, so bring down negative 2x. Then negative 2 minus 1 is negative 3. Now we can solve this by factoring. However, notice we have that coefficient of 5. So this is having to use bottoms up, where I've got x squared minus 2x minus 15 is equal to 0. Now I can factor. So here I've got negative 5 and positive 3 as my two factors that are going to multiply to get negative 15 and add to get negative 2. But then remember with bottoms up, whatever factor of A, what we multiply by, now divide by that value of 5. So then here you get x is equal to, well, if this is negative 1, that means you end up with x is equal to positive 1. And not positive 3/5, but negative 3/5. That is why, and if you were to graph this as well, you do end up with C. Because also when you check for the extraneous, which is plugging back into x plus 1 because the radical was by itself, so x plus 1, well, 1 plus 1 is 2, so that's good. And negative 3/5 plus 1 is positive 2/5. So both are a solution. So then in question number 9, same thing. See how here, oops, sorry about that. See how here we're solving again our radical. It's already by itself here. No need to move anything over. So I'm going to go ahead and square both sides. Then the radical cancels out, and I have negative 35 plus 12x is now equal to just x squared, because that was x by itself. But again, you're solving a quadratic, and quadratics always have to equal 0. So we need to subtract 12x from both sides, as well as add 35 here to both sides of the equation to cancel out and now have 0, which is equal to x squared minus 12x plus 35. Now we can go through here and solve for x by factoring. So what numbers multiply to get 35 and add to get negative 12? Negative 7 and negative 5. But remember, because you're solving, this is equal to 7 and 5. And then here, x was by itself, so can x be positive 7? Yes. Can x be positive 5? Yes. So here you end up with A. Now question number 10, or 10A, if you want to call it, and then we'll go to 10B. You're given the exponential graph. So we're going to select two that apply. Well, with an exponential, I notice here I have a horizontal asymptote at y is equal to negative 3, which means it's not A because this said vertical. And also because it's a horizontal asymptote, when I'm looking at my ends here, notice how the graph is constantly going to the left and constantly going to the right, which means the domain is all reals. So I'm going to mark off B. However, the range, now the y values are starting at the asymptote -3. Notice how the graph is going above, starting from that asymptote. So the y values are greater than -3, which does show here because of the positive infinity. So G is one of the answers. Then let's take a look here at the end behavior. As x decreases, right? See how this says as f of x approaches? This is then referring to, in words, the end behavior. So if it says as x decreases, that means what are we approaching, positive or negative? Well, negative infinity. Then that means f of x is approaching what? Now notice how C and D are both x is approaching negative infinity. So as we're going to the left here, right, as x is approaching negative infinity, yes, the graph is going down, but is it going all the way down to negative infinity? No. Remember, right, it's approaching but never reaching this asymptote here, this y value of -3. So f of x is approaching -3. So that's why the answer is C and not D, which means there's our two answers. Notice how the x-intercept, well, if the x-intercept was -3, then it would have been crossing over here. But our x-intercept is over here, approximately between 1 and 2. And this says f of x is positive for all x values less than -1. Well, if we're starting at the x values of -1, notice how here this section, oh, I'm sorry, less than, sorry about that. So because it said less than, we're talking about all these, which are negative values. Oops, sorry, I don't know why I just did that. Not positive, so the answer was only C and D. So then 10b. Now, which equation represents the exponential function? So again, always identify the y-intercept. So notice how here we're at 0, 6. So I need my y-intercept, so I'm going to cross out B and D. Then always read the direction of the graph from left to right. Notice how this is decreasing, showing decay, which means the base has to be less than 1. So that's why here the answer is D. Notice how the base 3/7 is less than 1 versus 7/3 is greater than 1, which shows growth. Then, of course, you can also graph in Desmos to check your answer. So now question 11. Again, we're looking for which statement is true about the exponential function. So again, here I've got my asymptote, my horizontal asymptote at y is equal to 5, which means, again, the domain is going to be all reals because the range starts at y values, which are starting at 5. And again, the graph is above, so y values are greater than. Well, I can already tell what my answer is because we're looking for a true statement. That's why the answer is D. Because remember, the domain, negative infinity to infinity, is the same as saying all reals. So like, for example, as x's are approaching infinity, as we're going to the right, f of x not approaching -5, they're approaching +5. Then here, as x is approaching negative infinity, as we're going to the left, notice how this is going up to positive infinity. So that's why the end behaviors are both wrong here. And these values are all positive, not negative. Now in question 12, they're asking for which question is false for this logarithm. So now with a log, remember it is the inverse of the exponential. So we're not going to have a horizontal asymptote, but now a vertical asymptote here at x is equal to 2, which means now the domain is what's cut off, right? Because now x values are starting at 2. And notice how we're going to the right. So all x values are greater than 2. However, this graph is constantly going up, slowly but surely, and constantly going down. So that's why now the range is what is all reals. So we're looking for false, so I can go ahead and mark off A because this is true. Now let's look to see the end behavior. As x's are approaching infinity, well, we don't have that. However, we do have two statements here. As x decreases, f of x approaches, right? So this is showing end behavior again. So as x decreases or as x approaches negative infinity. Well, are the x values going all the way into negative infinity? No. The x values are only approaching but never reaching 2. So as x is approaching 2, the end is approaching negative, or the f of x value is approaching negative infinity. So D is true, but that's why C is false, because the x values are not going all the way into negative infinity. They're approaching 2. And so now here we're looking at seeing which statement is true regarding our log here. So again, now notice if I'm talking about this equation of this log here, but I'm looking for visual, right? We need to know what is the end behavior, what type of asymptote. So again, graph this in Desmos. So let's first look to see what type of asymptote. Now keep in mind you have a log, so there should be a vertical asymptote. So let's check. And here you go. So notice how right here we do have that it's not horizontal, vertical asymptote at x is equal to 5. Because now notice how we are slowly but surely going up to positive infinity. So here, because of the vertical asymptote, we can go ahead and cross off C and D. So now let's check the end behavior. As x's are approaching infinity, right, as we're going to the right, what is happening to the f of x values? Well, they are increasing, going up and up and up to positive infinity, not negative infinity. That's why the answer here was B. And then question 14. We're looking for the inverse. Oops, sorry about that. We're looking for the inverse of our function here. And so now notice how we're given this original graph here, but we're looking for the inverse. Now, I notice that I don't have an equation, but I can locate points on my graph. So like I notice, for example, here at 20, 16, I have this coordinate. I also have coordinates here at 8, 12. I also see another coordinate right here at 2, 6. Because again, notice how, see how it went to 10? That means each of our grid lines are counting by 2. So keep that in mind too when you're looking for what you're counting by. So now if I'm looking for the inverse of the graph, so this means, remember the inverse, we switch the domain and range. We switch the x and y. So the inverse function is not going to have the point 2016, but it's going to have the point 1620. It's not going to have the point 812, 12.8. It's not going to have the point 626, 6.2. So now I can go ahead and start plotting to see, well, which of these graphs have these coordinates. So here, 16, so 10, 12, 14, 16, 20 is on the graph. 12, 8, so 12, 8 is on the graph. 6, 2, 4, 6, 2 is on the graph. So that's why A represented the inverse of our graph here.